Hello, and welcome back to the course. So today we're again looking at non-homogeneous equations, and we'll look at the second part of this section, 2.5 in the book, which is on variation of parameters. So we're looking at another way to solve non-homogeneous equations. And the book is at this URL. You can get a PDF, you can browse it on the web, or you can get a paperback if you want. All right, so we're still trying to solve this equation where L is a differential operator and F is some function, some right-hand side, some non-homogeneity over here. And well, undetermined coefficients is relatively easy, but it requires one thing about F, and what it requires is that when we start taking derivatives of F, that basically we are getting kind of the same thing or same sort of thing, that they all have the same general form, where we have a bunch of constants that we can solve for. But that's not true in general for many f. So for example, let's look at what if f is the tangent, right? So f is the tangent, so f prime is secant squared, f double prime is 2 secant squared tangent, then this f triple prime, f, the fourth derivative and fifth derivative. It just gets worse and worse. There's no, each one of them is different. We cannot find some general form here that will just work for all derivatives. So that's something that we would need for undetermined coefficients. So undetermined coefficients is not going to work when the right-hand side is a tangent. Okay, so all right. Well, what is going to work is the so-called variation of parameters, and this can this can handle almost anything. But the computations can get rather tedious. I mean, in the end, you have to do some integrations and whatnot. Right. So it's a little bit more tedious maybe, but it can handle more stuff. If you can do undetermined coefficients, you probably want to do undetermined coefficients. All right. So we will stick to second order constant coefficient ODEs, but really, linear ODEs it will work for, provided that you can somehow get the complementary solution to the homogeneous version, right? The associated homogeneous equation, right? So for example, if we're second order, so we have that this linear operator Ly is 0, right? That's the homogeneous equation. And suppose that our general solution there is, well, I mean, we found two linearly independent solutions, y1 and y2. And so by taking a superposition of them, we have the general solution, right? So that's this thing is when we plug that into L, it just disappears. It solves this equation. All right, well, so we're going to look for a solution of the non-homogeneous version by, well, basically taking this, and instead of constants in there, we're going to try, well, could we solve for some functions u1 and u2 instead of constants, right? So that gives us more flexibility, and maybe we can do that. And it actually works. So basically, we just take the complementary solution, and instead of constants, we plug in functions, and now we're trying to solve for those functions, right? So let's see an example. It's probably easiest to see an example. So let's suppose that we have y double prime plus y, and you got tangent x. So the complementary solution is easy. In this case, it's sine and cosine. So this is what it is. So maybe y1 is cosine, y2 is sine. So what we're trying to do is u1 some function times cosine plus u2 again some function. These are not constants; these are functions times sine, right? So that's what we're doing, right? So u1 and u2 are functions of x. All right, so we have to somehow plug it in. So we have to, well, we know what y is, but we need to figure out what y double prime is. So we need to differentiate. So let's do y prime. Okay, so it's just a product rule, right? So from this guy, I get this and this, but I've grouped it in this way, and from this guy, this and this, right? So I'm just grouping it in a funky way because we're gonna do something with this. I mean, this is already getting complicated now. Imagine if we, you know, differentiate it again. You have to do product rules again for all of these. That might be complicated. So the idea is, well, I mean, we have two unknowns, right? But we're really imposing only one condition so far. I mean, it has to solve the equation, right? That's what we want, right? It has to solve this. So maybe we could impose another condition to make things simpler, right? And so we do that. So we basically, what if this guy over here, what if that just wasn't there, right? That just means that that thing is zero. So let's just assume it, right? So we have two conditions, this one and this one. All right, because then y prime is just the second term over here. All right. So okay, let's go on, right? So we start with this, and we differentiate, right? So we're assuming already that y prime is that's this guy, right? So we differentiate again, we get you know we use product rule, right? So our product rule, the product rule for this first guy, again, I'm writing it like this. This becomes this and this, right? And you know the other two terms are for the second term in the y prime. Okay, so now still want to simplify a little bit. Well, turns out we can, we can do something over here. So y1 and y2 are solutions to the associated homogeneous equation, right? So in this case, it is actually fairly simple, right? But this sort of argument actually works for, doesn't really matter what the left-hand side is, right? But our left-hand side was y double prime plus y is 0. So y double prime is minus y, right? So that's true for y1 and y2. So we could plug that in. And we get this, right? So this thing becomes this. Well, that's just it's just y, right? That's what y is, right? So what we get is y double prime is this thing minus y, right? And now we can move that to the other side, right? And you can see how that would work in for a more complicated L, right? So you can try that for a slightly more complicated L, right? Maybe make it y double prime plus 2y prime plus 3y or something, right? Do that, right? And you'll see it works the same. Okay, so way over there. So now on the left-hand side, we have the L, right? The linear operator. And on the right-hand side, what we have left is this guy over here, right? So, well, we want y to be a solution. So then this thing had better be f of x, whatever that is, right? And so now we have our second equation, right? That this guy had better be f of x. So let's write down the two equations that we have, right? This thing was the thing that we imposed arbitrarily, and this thing is the thing that comes out from this had better be a solution. All right, so that actually looks pretty nice, right? I mean, it's, there's no u's, u1 and u2, there's only their derivatives, right? And okay, so I have y1, y2, y prime, and y1 prime, y2 prime, but this should be fairly easy to solve for u1 prime and u2 prime, right? If there's just this 2 by 2 linear system, right? We can just do that algebraically, right? Now, once we have u1 prime and u2 prime, we can integrate those, find some antiderivative, and once we have u1 and u2, we just plug that into the formula for y, and we have a solution, right? So let's do that on an example, on the example that we're doing, right? So we have cosine and sine, right? So this is the y1, this is the y2, right? y1, y2, y1 prime, y2 prime. Okay, and that's where the minus sign comes from, right? From differentiating the cosine, right? And this was f of x, right? So that's what we have. So how do we solve it? Well, let's maybe eliminate u1 prime, right? So that requires multiplying the top thing by sine and the bottom equation by cosine, right? So if we do that, right, this is the top equation, this is the bottom equation after we've multiplied, right? And now you notice that if I add those two equations, right, this thing cancels this thing, right? So I will just add this plus this is going to be equal sine, right? Okay, this plus this, that's this guy, and sine squared plus cosine squared is 1, so that goes away. That's rather convenient. I mean, if it didn't, I just have to, solve it, right? I mean, it's not that's not a big deal. It's just in this simple example, it's actually simple. So I just get that u2 prime is just sine, right? Well, if u2 prime is sine, u1 prime, well, it's a little bit more complicated, but I could go with this thing, right? I could look at the first equation and solve for u1 prime. Now I know u2 prime, right? So I just solve for u1 prime in this equation, and that just gives me this, right? And another way of writing that is it's cosine minus secant. All right. So that gave us u1 prime and u2 prime. So we need to, if we want u1 and u2, we need to integrate, right? And well, we just do the integration. It's just calculus, right? So we just find antiderivatives, right? So the antiderivative of cosine is sine. The antiderivative of secant is this guy over here. There's a bunch of different ways of writing that, right? If you remember, but yeah, let's write it like this. So that's our u1. Maybe it's a little complicated, but oh well, that's what it is. u2 is just the antiderivative of sine, so it's minus cosine. That's a little nicer, right? Well, we're not still done yet. Yes, still write down y. Now you'll notice that I didn't put the plus c over here, right? Well, you could. If you put the plus c, you will actually, so there's going to be plus c1 over here and plus c2 over here, let's say, right? Because you have two constants of integration. They should be different. If you put them in there, you will actually get the general solution to our equation. But at this point, we're just looking for a particular solution, any particular solution. We're not worried about what initial conditions is satisfied or whatever like that. So we're just going to ignore them, ignore the plus c's, right? So that's RU1, that's RU2. So we just plug in, right? So a particular solution is U1 times Y1 plus U2 times Y2. And that's just, if once you work it out, that's what it is, right? So, that's just plugging the thing in, right? This actually nicely cancels out, so it's actually kind of simpler, right? So cosine x times the logarithm of secant plus tangent. All right. So that means that the general solution to Ly as tangent of x, so y double prime plus y is tangent of x, is, well, you put in the associated homogeneous, the solution to the associated homogeneous equation, the complementary solution, and then you add the particular solution, which is this, right? And you can see that if there were constants over here, constants of integration, then they just end up over here, right? I'd get C1 times Y1 and C2 times Y2, right? So anyway, that's the solution. So what's the procedure, right? At least for second order, right? For variation of parameters. First, well, just like for undetermined coefficients, you find the complementary solution, and then you solve for u1 prime and u2 prime in these equations. Then you integrate to find u1 and u2, and you find your solution, right? Your particular solution, right? Now, the undetermined coefficients technique is usually a little less tedious if it's possible, if you can actually do it. Because I mean, we did a very simple example, but if it's a little bit more complicated, then some of these computations can get a little little harder, and that integration might get a little harder to do. Undetermined coefficients is very straightforward if it works. So do that if you can. If you can't, okay, you have to do this if you really are looking for a solution. All right, so we're gonna look at that. So next time we're gonna actually try to apply non-homogeneous equations. So we're gonna look at the mass spring setup that is forced. So we're gonna have a non-homogeneity in there, right? So we're gonna have some forcing function, and we're gonna look at what happens then, and in particular, we're gonna look at resonance, right? Okay, so right, so see you then.